the next talk by Frank Deppisch from University College London, who will teach us how to search for sterile neutrinos.
Yes, thank you very much. Let me share my screen, which I can do now, I believe. So thanks a lot for the invitation. Obviously, I would like to do this in person, and ideally last year, right? So when also the topic was set. So the title I called this and kind of agreed with the organizers was Searches for Sterile Neutrinos. But I also have a kind of slightly different angle in a sense that my kind of main research is in terms of neutrino style beta decay. And because we specifically kind of in this session here, we already have very good talks about this intensity frontier, of course. So in this regard, I'm not going to add too much, but essentially I would like to kind of contrast these kind of direct searches, expand them also a little bit, kind of highlight that there's kind of for larger masses of sterile neutrinos and kind of lighter masses also searches there, but also contrast this with neutrino style beta decay as an indirect search essentially, and see how this kind of connection works. Okay, so also apologize, I've called them always sterile neutrinos. I understand most of you kind of using this NHL nomenclature. I'm not quite sure really actually what the difference between them is, right? But for me, they're essentially the same kind of thing. Sterile neutrinos, right-handed neutrinos, which essentially just have a coupling to the standard model via their mixture with the active neutrinos.
Okay. There is no difference. It's just because cosmologists like to use this name for various anomalies in their observables that they have. They like to call this sterile neutrinos, and that's why.
Okay. So the main motivation behind all of this, at least I mean for me and for I think the majority of researchers in this area, is the question about whether neutrinos are Dirac or Majorana, right? So all these searches for heavy neutral leptons or sterile neutrinos are kind of motivated in a sense that they try to understand or they try to explain the lightness of neutrinos via some kind of modified seesaw mechanism in a way, right? So implicitly, it is kind of always assumed that the active neutrinos we have in the standard model are Majorana, okay? Of course, this is not the only possibility, right? Just like the other leptons, the charged leptons, the neutrinos could acquire a Dirac mass, right? Again, we would have to introduce a right-handed state. That is the kind of thing, right? But we could introduce a Yukawa coupling, which is very small, which would then kind of explain the lightness of neutrinos. This is not very natural, and from a theoretical point of view, we also would have a problem in a sense that this is the kind of interesting kind of feature of this right-handed neutrino we have to introduce, is that it would be completely uncharged under the standard model gauge groups, right? So it would be natural and would be kind of natural that it has its own kind of Majorana mass. Nothing prevents it for this to acquire such a mass, right? So even in such a scenario with Dirac neutrinos, one theoretically, it's not very satisfying that the right-handed neutrino doesn't have a Majorana mass. We would have to impose, for example, a B minus L symmetry, for example, right, which would then be unbroken, right, whether it's gauged or whatever, right. So this is something which would go beyond the standard model also. Okay. Now, implicitly, as I mentioned, behind all the kind of models we are discussing in terms of heavy neutral leptons or sterile neutrinos, or any other kind of physics beyond the standard model, typically at the TeV scale, which kind of tries to explain the lightness of neutrinos, it comes through the feature that we understand active neutrinos to be Majorana fermions, right? So that's kind of very basic picture from Weinberg, that we can deal with them even without introducing a light right-handed state, right? That we have an effective operator beyond the standard model, the Weinberg operator, in which we understand the generation of the light neutrinos as a suppression of a very kind of heavy new physics, which introduces this Majorana mass for the active neutrinos after the electroweak symmetry breaking. Okay. So from this point of view, we see that the neutrino masses or the origin of neutrino masses are crucial for beyond the standard model physics. So again, kind of as I already mentioned, so a crucial role as part of this is the total lepton number symmetry, which if neutrinos are masses, it arises accidentally as a global symmetry in the standard model, right? We already know that it's broken non-perturbatively with B minus L remaining conserved. one could then imagine, right, even if there is a global symmetry like this, whether this should be broken by gravitational effects. So even without any kind of seesaw mechanism or whatever, right, you could naively kind of expect that if P minus L was broken at the Planck level, right, it would introduce a neutrino mass of the order of 10 to minus 5 electron volt, right, which is again a kind of conundrum. This is too small to explain oscillations, so this cannot explain the neutrino oscillations we observe. On the other hand, it's too large to be some kind of subdominant splitting, right? It could be something that the active neutrinos are kind of quasi-Dirac states themselves, right? But a mixing or splitting of 10 to minus 5 is too large for that. From solar oscillations, actually, this would be already kind of ruled out, okay? So this is just to motivate, this is a kind of conundrum we have, that we don't understand the nature of neutrinos. So no matter what we do, right, Dirac or Majorana, we need to kind of have some other kind of means to probe them in a way, okay? So as I said, my angle, I'm coming from neutrino style beta decay. I'm not going to go into detail here, right? I just want to mention, so to say, that this is the kind of, at least from my point of view, the kind of, as far as the active neutrinos are concerned, the crucial process to understand whether they're Dirac or Majorana, right? If neutrinos were Dirac, then no neutrino style beta decay would be induced, right? Lepton number would be conserved, right? Neutrino style beta decay concerns the emission of 2 electrons out of an initial state which doesn't have any lepton number, right? So obviously the process violates lepton number by 2 units, right? And via the light neutrino exchange, it probes the so-called effective neutrino style beta decay mass, I'm pretty sure, which you've heard about, okay? And without going into all the details, right, I mean, this is very kind of complicated nuclear physics with all the nuclear matrix elements coming in, which has some uncertainty in there, right? But the general argument remains, if we were to observe this process, then we would know that the active neutrinos would be Majorana fermions, right? They would be Majorana particles, okay? And this would essentially, of course, have immediate kind of consequences for all the searches you would be doing at the intensity frontier, for example, right? And the kind of scale we're probing is of the order, I mean, this makes it kind of practically interesting, of course, is that the current kind of sensitivities, which are around 10 to 26 years of half-life of this decay in certain isotopes, right, probes this double beta decay mass of the order of electron volt or 0.1 electron volt, right? So we're kind of reaching the kind of scale, which is also kind of imposed or kind of limited, like for example, from cosmological kind of observations, but also kind of not predicted, but kind of consistent with the kind of scales which we observe in oscillations, right? Now this picture is probably a little bit different, right? So essentially what it shows here is this kind of what you might have seen, right? You might have seen double beta decay kind of correlated against the lightest neutrino mass. So what is correlating it here is this effective observable in double beta decay with the sum of neutrino masses, which is essentially what is kind of cosmological kind of observations are sensitive to, right? And so the current kind of limits here by this upper kind of red band, that is the kind of current sensitivity. The band itself gives you an indication of what kind of errors are in there, right? So these are sizable, right? But double beta decay essentially limits this effective double beta decay mass of around 100 milli electron volt, right? So in future searches, they expect to go down essentially to probe the so-called inversely ordered scenario, right? Double beta decay is not a kinematic measurement, right? So this is not like single beta decay where you measure the mass of the neutrinos kind of explicitly or directly, right? The neutrinos are involved as a virtual exchange, so they all contribute. So they all kind of, all 3 active ones at least, right? They all can contribute, and via kind of cancellations, you get this kind of large kind of variation of these areas, right? Specifically induced by the so-called Majorana phases, right? And it also depends on the order of the neutrinos, right? From oscillations, you know that at least at the moment it's still possible that they are either normally ordered or inversely ordered. With the inverse ordering already kind of being disfavored from oscillation experiments, right? Which is a bit of a problem for double beta decay, right? Because the inversely ordered scenario has a higher kind of rate for neutrino style beta decay, as you can see in these regions, IO and NO, right? But I should point out that future searches, which go down to 5 times 10 to 26 years in molybdenum, for example, or 10 to 28 years. This is very far future. This is not like in 5 years or so, but germanium, right, could go down to that level, and they're designed to probe this inversely ordered scenario, right? Of course, you might then ask, so if it's not inversely ordered, does it help, right? I say it does, right? So as you can see here, so even in the normally ordered scenario, these future searches are going to probe a sizable chunk out of that, okay? The problem with normally ordered that you always have this possibility that all contributions completely interfere, right? It's accidentally possible that M beta beta becomes 0 for a specific choice of the light neutrino masses, right? But in this kind of way of plotting it here, at least on a linear level, right, this occurs only in the kind of very small kind of part of the parameter space, okay? Now coming to the sterile neutrinos, obviously, if you probe the Majorana nature, this immediately has an impact of what we're looking at, right? If double beta decay were to observe, were to be observed, right, we would know they're Majorana, right? And we would need to kind of understand what the nature of the neutrino mass mechanism is, right? But in addition to this, sterile neutrinos can also directly contribute to neutrino double beta decay, right? So this works in the same way. It's the same diagram, which is often nice for double beta decay. You don't have to kind of draw too many diagrams usually. The shape is always the same, right? But instead of having a light neutrino being exchanged here, you can have a sterile neutrino, right? If the sterile neutrino is much lighter than the typical scale of the process, which is 100 mega electron volt, right? Because we're looking at the nuclear scale, then this sterile neutrino acts like a standard neutrino if you want, right? So it contributes linearly to the amplitude, right? It kind of is an additional contribution to M beta beta. On the other hand, if the sterile neutrino is much heavier than 100 mega electron volt, then it would essentially contribute via the propagator of this guy inversely with the mass, right? So effectively, you get again an effective kind of parameter here, but this is essentially kind of regulated by the mixing of the sterile neutrino with the active ones, which is called here VEI squared, right? And then being suppressed by the mass of the heavy neutrino, right? So this is effectively the parameter you're kind of probing here, okay? And this is again very simplified, right? I'm going to contrast this here. If you just look at the contribution of the heavy neutrinos, this is how it would go, right? But what is possible is again this nature or the possibility that the nature of the sterile neutrinos could be quasi-Dirac. Then there's kind of cancellations happening among this here, right? And it is also possible to have kind of cancellations with the contributions of the light neutrinos. And this is actually very natural, right? Because if the heavy neutrinos contribute to or are responsible for the light neutrino mass generation via tree-level kind of seesaw scenario, then if the neutrinos are lighter than 100 MeV, then actually their contribution is expected to cancel exactly, so to say, right? So the light neutrino and the heavy neutrino contributions, they cancel exactly in such a scenario. So this is important for the later discussion then, right? So as I was pointing out, we have very many different kind of ways of dealing with this, right? The standard kind of scenario of neutrino mass generation is the seesaw mechanism, right? That we have essentially heavy Majorana neutrinos in the standard picture, of course, possibly living at the gut scale, right? But what you are all interested in, or what you'd be interested in as phenomenologists, is to have these heavy neutrinos around the TeV scale or lower, right? So we then actually probe them. But then the problem in order to understand the lightness of neutrinos is that their mixing with the active neutrinos needs to be very small, right? If the mass is around TeV, the mixing needs to be of order 10 to minus 6, right? And with all observables in some sense going like mixing squared, right? It goes down to 10 to minus 12 in the mixing squared, okay? There's a way around this, and I'm pretty sure you've heard this also, right? And this is kind of imposed or kind of used, for example, in the minimal neutrino standard model also, right? Which we call the bent seesaw mechanisms, right? Because this kind of relation of the light mass going down and the heavy mass going up, right? In the standard seesaw is no longer kind of correct, right? It also goes by the name of kind of symmetry protected seesaw mechanisms. Essentially, it boils down to kind of decoupling the scale where lepton number is violated, which is always the source of neutrino masses or Majorana neutrino masses, from the heavy neutrino masses themselves, right? So phenomenologically, what happens is that the heavy neutrinos become quasi-Dirac, the protection of lepton number, which is needed to get the light neutrino masses correctly, then corresponds to essentially to a small mixing between the Majorana, between the heavy neutrinos. Okay, so we have analyzed this. This is nothing new, of course, but we have analyzed this in kind of very simplified scenario, kind of forgetting about different generations. So we were just interested in the electron flavor, and then having introduced two sterile states. So we have in some sense a freedom of introducing, or what we impose, so to say, is the most general kind of mass matrix one can write down in such a case, right? With one active and two sterile ones. And what we want to do in some sense is kind of parameterize the general behavior between these kind of limiting kind of scenarios, right? The heavy neutrinos are perfectly Majorana, and on the other hand, so to say, the heavy neutrinos are kind of really quasi-Dirac with a more small mass splitting between them, right? And so with this phenomenological parameterization, this allowed us to kind of look at the behavior in between, right? And I mean, I'm not describing this so much in detail because I don't think I have so much time anyway, right? But what is possible, so to say, one can infer, so to say, or one can relate the mixing of the active neutrino to one sterile neutrino and the other sterile neutrino. That's the parameter space essentially we're looking at. And one can see how this behaves. And so the different scenarios are given, or the limiting behavior is given by the edges of this. So for example, this bottom left edge is essentially like the standard Majorana case, right? So if you go down to the bottom here, this would essentially just mean that the active neutrino just mixes to one sterile neutrino, right? Here it mixes to the other sterile neutrino. So at the edge here, it's essentially an intermediate kind of scenario, okay? And if you go to the top right, that is a scenario where the mixing can become very large individually, right? And that is the scenario essentially where the heavy neutrino becomes quasi-Dirac, okay? So what is indicated here in some sense is the mixing angle between the sterile ones. And this can also be inferred, for example, from the CP phases, which is there, right? In such a case, you would have in the CP conserving scenario that the two sterile states have opposite CP phase, right? Such that they essentially kind of form a quasi-Dirac pair, okay? And this allows us to have the intermediate kind of ranges as well, okay? Now, talking about sterile neutrino searches, it's impossible to kind of cover all of this here, and the kind of important ones as far as this kind of workshop is concerned are being covered very well here, of course, right? So the constraints to the coupling to the active neutrinos here, with the active neutrinos, or the mixing of the sterile ones with the active ones, comes from a large number of experimental observations. Okay, I'm going to show a kind of more important or bigger plot later on to kind of highlight this a bit, right? And many of the aspects have already kind of mentioned, right? So if we talk about production, like in meson decays or the collider, for example, right? What becomes important is that sterile neutrinos can be long-lived particles in a very interesting regime, right? Because the mixing is small, their masses are kind of small, right? Because it's suppressed by the W and the Z boson mass, right? And also what we are talking about here, right? Because we want to find out the nature of things, is that if these sterile neutrinos are kind of produced resonantly, then actually it is also kind of quite kind of relatively easy to see lepton number violation, because the suppression of lepton number violation, if they're quasi-Dirac, it should be suppressed, right? In the limit that they become perfectly Dirac, lepton number violation goes to 0. But if they are resonantly produced, this suppression is only regulated by the small width, right? So what is kind of important is delta Mn over gamma n in such processes. And this is different from double beta decay, for example, where gamma n does not really play a role, right? So as we will see, double beta decay is much more suppressed if the splitting is small than the resonant production in meson decays, for example, or at colliders, right? So what we have produced in some sense is this kind of big kind of overview plot. Again, I'm not going to go through all of them here, right? So the kind of main kind of interest you're going to have is essentially around the 1 to 10 GeV kind of range here. So these are the current limits. This is purely for the electron kind of picture, right? For one generation here. Again, this is the kind of not downside, right? But that was our choice because we wanted to compare to double beta decay. If you're interested in kind of a general fit, you can look at this paper here, right? Which includes kind of 3 generations of neutrinos and active neutrinos as well, right? But it essentially kind of shows the kind of big range going all the way from, let's say, 1 TeV at, of course, the high energy colliders, right? Then to kind of meson decays, right? Here to lower energies, we have kind of better decays. There's a kind of large field here, and I would like to kind of highlight this also a little bit later. So better decays, they cover essentially this kind of region between MeV all the way down to a few electron volt, right? Depending on what the Q value of the better decay is, right? So at the lower end, for example, it's tritium decay, which in itself is, of course, an important kind of probe of neutrino masses here. And then all the way to the very bottom, you have essentially kind of neutrino oscillations, right? Which also kind of probe sterile neutrinos, okay? And also overlaid here, but this is, of course, always a bit difficult to compare, right? So we're not claiming this is kind of perfectly kind of calculated consistently. And we essentially took these limits essentially just from the literature, right? We didn't do anything kind of fancy with them. It's all the kind of limits from cosmology, like Big Bang nucleosynthesis, right? So the impact of the sterile neutrinos on this. Also the kind of nature of if the neutrinos would form dark matter, right? That the kind of chunk of this parameter space is ruled out, right? And also the impact of sterile neutrinos, essentially by looking at the effective number of degrees of freedom, and the mass of the neutrinos, right, which is being probed by cosmological observations. They essentially kind of not rule out, right, but like the organizers kind of made a question whether what should we do with these limits, right? But this simply indicates that cosmological observations are kind of sensitive to these areas specifically, right? Which is, of course, a big kind of motivation to look for heavy neutrinos essentially above this scale of around 1 GeV, right? And also, of course, motivated then that it's possible kind of solution also for the baryon symmetry of the universe, okay? So these are the existing ones, and again, we kind of collected, so to say, what the kind of future ones are. And as you, of course, as you know, it's kind of this crowded field of intensity and kind of long-lived particle searches here, which are around a 1 GeV to 100 GeV kind of scale, possibly, right? Indicating what these limits in the future are. Okay. So as I said, what I would like to contrast is with double beta decay, right? And this has been always a kind of long discussion, I think, is that if in the kind of neutrinos double beta decay community, what people are doing is they just show the limit of the heavy neutrinos themselves, right? And so you simply have this kind of band here. I think you can see my cursor, right? So this would be the limit you would get. Anything above that would be ruled out, right? So the claim would be, we just do double beta decay and we don't do anything else, right? It rules out everything. But this is, of course, theoretically not consistent, because if we had such a heavy Majorana neutrino, it would actually induce a light neutrino mass, which would be too high, right? So we would need to modify essentially the mechanism of neutrino mass generation. And we would do this essentially by making it quasi-Dirac, okay? So what the benefit of our analysis is, in some sense, that what we can put in is the light neutrino mass, which shows us 10 to minus 3 electron volt here as an example. It doesn't really change so much, right? And using this channel parameterization we used, right, we can essentially calculate all kind of contributions consistently, right? The mixing and so on is kind of inferred backwards. Sorry, it's a bit hard to explain, right? But so to say, every point in this parameter space is consistent, right? It produces a light neutrino mass of 10 to minus 3 electron volt, is kind of what I'm saying, okay? So you can produce this essentially almost Majorana-like, where this kind of band corresponds to a kind of splitting between the two sterile states of order 10 to minus 2, then 10 to minus 4, and 10 to minus 6. And as you can see here, the neutrinos double beta decay kind of limit kind of is reduced drastically out of this, okay? The one important thing I should mention in addition to this, so there's a theoretical kind of consideration on top of that. So while, for example, this kind of splitting of 10 to minus 2 is consistent, What it would also induce is that there's actually a large loop contribution to the light neutrino masses, okay? So this contribution is only at the tree level. So if we are in a kind of regime where the heavy neutrino mass is large and the mixing is kind of large, sorry, in this kind of upper right edge here, in such a scenario, starting with the seesaw matrix, with the general seesaw matrix, what you then also get is contributions to the light neutrino mass via loops, okay? And in this regime, they become very sizable, okay? And so this is indicated by these kind of lines here, right? So everything to the right and to the top of these lines would be kind of not ruled out, but it would induce a loop contribution which is 10% of that of the tree level, right? So this is not theoretically ruled out. It's possible that there's a sizable loop contribution here, right? But if you're interested in a scenario which is mostly like the tree level seesaw, right? And we want to regulate them, of course, right? If they would be about 100%, then it becomes kind of non-perturbative in a way also, right? So we can't really calculate the neutrino masses. So from a theoretical point of view, anything to the right of these kind of lines here would be disfavored because the contribution to the light neutrino masses becomes too high from loop contributions, okay? So as you can see here, this kind of, well, the larger the splitting is, right, the more effective or the higher these loop contributions are. So, right, so if I want to concentrate on this 10 to minus 2 splitting here, so I would essentially say that, okay, neutrino star beta decay can be kind of competitive for masses around 1 GeV, maybe 10 GeV or so, right? Masses above this would induce too high contributions via loops, okay, to the light neutrino masses, which makes this no longer consistent. Okay, so these were the current limits. These are the future limits for neutrino star beta decay, right? So it becomes more sensitive, of course, right? But this is nothing new. And finally, I would just like to point out, right? So this kind of splittings we discussed before, they were essentially very small, like of order 10 to minus 2, 10 to minus 4, and so on, right? So it's perfectly possible, it's maybe not very natural or anything, right, to also consider a large splitting between the two sterile states. So the green band, for example, this corresponds to a splitting of order 1, right? So for example, I don't know, one of them is 1 GeV, the other one has 2 GeV. And it's perfectly possible to get the light neutrino mass correctly. And as I said, right, the loop contributions become sizable, right? But they are still kind of only become dangerous in this kind of area here, okay? So in this kind of region, it's still possible to have kind of perfectly normal kind of light neutrino masses of order 10 to minus 3, only corrected by 10% by loops, right? And you get a sizable contribution to neutrino star beta decay, which is competitive essentially to kind of direct searches in this 1 GeV mass kind of range, right? If the splitting becomes larger and larger, and this becomes very unnatural, right? We're talking about a splitting of 10 to 4, right? So one of them is very light, and then the other one is like 10 to the 4 orders of magnitude heavier, right? It's phenomenologically possible to do this. The loop contributions become very sizable and rule out a kind of chunk in this area, right? But it is possible to have neutrino star beta decay become sensitive in this area as well, okay? So I think that is essentially the kind of main message I would like to come across, right? To give you this angle with double beta decay, which I think is important. And because I saw this kind of message by the organizers, right? So what do we do? Should we, for example, conduct searches in laboratories where, for example, in areas which are ruled out by, or not ruled out, but kind of disfavored by cosmology, let's say, right? So my thinking is that, yes, we should do this, right? Because I think this is simply a different quality if we do in the laboratory. And the ones I would like to point out, again, this is a bit outside, of course, what your community is kind of interested in, is to kind of extend this to lower masses as well, right? I'm sorry, if I just go back to this quickly, right? If we talk about 1 GeV, this is dominated like meson decays, of course, right? But as I said, if you go to essentially like a 1 MeV, right, or a few MeVs, hundreds of KeVs or so, this becomes kind of dominated by beta decays, and which are the only kind of searches, right? And I would just like to point out two additional kind of things, right? One thing we looked at is that we can actually use 2 neutrino double beta decay. So just like you look for kinks in single beta decay, You can also look for kinks in 2 neutrino double beta decay, which is kind of a bit crazy, right? But because neutrino double beta decay is kind of searched so intensively, right? We're going to have kind of sensitivities down to 10 to 28 years. We're actually going to observe 2 neutrino double beta decay, which is the standard model allowed mode, right? With very high rates, okay? And this allows us also to search for heavy neutrinos in there, right? So this is not Majorana nature. This also works for Diracs, for example, right? And the other one recently I saw is that there's actually a large kind of improvement possible in single beta decay also, right? So these experiments are not really expensive, I think, right? And they're not kind of conducted. There's not a big money behind that, of course, in some way, right? So there is a lot of kind of possibility to improve these in the future, right? Up to 1 mega electron volt, right? So this is then to the right here would be the kind of areas you would be interested in, right? But for example, recently in beryllium, using superconducting quantum sensors, what they claim, all right, to look for single beta decay, or rather electron capture, it is actually in this isotope. One can improve the limit on the mixing squared by almost 2 orders of magnitude, right? So there is a potential in such a parameter space or kind of mass region for the sterile neutrinos to improve the sensitivity in the laboratory, right, quite significantly. Okay. I think I'm not quite sure. I didn't look at my watch. I think I'm over my limit anyway. I think. So I'm just going to leave here my conclusions here. I don't know exactly how much time I would have available, but I'm just going to.
Yeah, I think you are over time already. Yes.
Right. Okay. That was my feeling. So I'm going to leave my conclusions here, and I thank you for your interest.
Okay. Thank you very much. Any questions?
Is it possible to show again this plot with a very large range for neutrino mass from 1 electron volt still and with very this one. Am I sure that the regions which is here is the BBN, okay, and this black line, okay, and another one goes from 1 GeV and another from 10 to -3 GeV, okay, and then goes upwards, yes, and all this region is excluded from BBN, yes?
To be honest, I'm not quite sure.
Yeah, but what does it mean, BBN here?
I mean, this right limit, this is BBN, right?
Okay, so what is below is excluded, yes?
Yeah, but what BBN?
It is my understanding, yes. I mean, I'm not an expert at this, and I'm not quite sure whether this whole parameter space has been kind of really completely covered in the literature in a way, right? I mean, in this region, it's kind of ruled out that the neutrinos themselves become so long-lived, they become essentially contributions to the effective number of degrees of freedom, for example, right, and specific regimes. And well, if they decay, then also they populate with the active neutrinos again, kind of inducing this, right? Whether this whole parameter space is ruled out, I don't know.
Okay, then another region which is another line CNB plus BAO plus H naught. What is this?
That is essentially the effect I mentioned. Yes. Yeah.
So yeah, but which region is excluded?
Well, we kind of assumed it's everything in between. I mean, these two lines come from 2 different analyses. These 2 lines come from 2 different analyses, right?
Yeah. So and you assume that what is in between is excluded, yes, from pathology.
Yes, I mean we assumed it. I mean we indicate it here. We don't explicitly kind of make that claim, right? But it is my understanding, right? But again, I'm not an expert in this. I don't know whether there is some kind of parameter space. I don't know, Fedor, you kind of nodding your head. I think you've been looking at this, right?
I'm not completely sure, but I also wanted to ask if I forgot this region from. But my feeling is that this is, as Dima is saying, something that's included from cosmology. Basically, I pretty nicely understand the lower line, the lower part of this CMB plus BAO plus H0 region, which is clearly the amount where this neutrinos will be rather stable and give you amount of energy density equal to the dark matter density in the universe. So basically, for some time going above this line, this universe will not look like ours. We'll have too much dark matter in neutrinos. When you go further and further up, slowly you'll get to the fact that the universe will be just overclosed. Then at some moment it stops. I'm not very sure where it stops exactly, but I suspect that this whole region is strongly disfavored from cosmology unless you do some really clever tricks with models. We with Dima are guilty in doing these tricks, but that's a very good question. Probably we should move this to discussions in the evening, because this is exactly one of the questions.
I mean, I would be interested in this experimentally kind of laboratory region, of course, right? So if the mixing is large, my understanding is that the neutrinos decay, right? But they still induce, or they still implant essentially effective degrees of freedom from their decay, right? So even in this large mixing regime, right, where they could be kind of, they're possibly not long-lived at the scale of the universe, maybe, right? So this would be still ruled out, right? But I'm not sure how completely this has been analyzed. I think this would be an important question for experimentalists.
So we looked into this in some detail down to like 10 MeV, so together with Marco Hufnagel and Valerie Domke. And it turns out that there's a whole bunch of constraints for cosmology. It's not just BBN, there's also photo dissociation after BBN, all these kind of things. So we didn't go down to all the very small masses, but for the mass range that we did look into, you have to go to some insanely small mixing angle, like 10 to the minus 20 or so, in order to not be ruled out. And then you basically just not ruled out because these guys are never produced.
Marcos, sorry, but photo dissociation after BBN is one of the, I mean, it's part of BBN bounds, right? It's a kind of BBN bounds because your observable is the same, because your bound comes not from BBN, your bound comes from primordial abundances. Right? Photo dissociation.
You can classify things in terms of, So it comes, you can call it BBN. So when I say BBN, I meant the direct impact of BBN, but of course there's photo dissociation, then there's impact on the CMB. So there are many different observables, and we found that at least down to 10 MeV, there's no hole in the parameter space unless you make the mixing so crazily small that the particles practically are never produced in the early universe. And you can call it, of course, you can call it BBN because it's the same observable, but it's not what we found. But combining what we found in the literature plus some other bound that we derive ourselves, is it becomes like a mosaic of bounds that closes down everything down to, in our case, I think minus 20 or so.
Yeah, we recently had a paper about effect of HNLs on N effective in different regions. I don't know, maybe Maxime will say a couple of words about this. I don't know. But I wanted to comment on this supernova region. I mean, for me, it pretty much does not exist, because to put any bounds from supernova, you need so many assumptions about neutron stars. There is not a black hole. What are the parameters of this neutron star? Then how do you interpret the signal with detected neutrinos from supernovas? So I personally don't believe in any bounds in sterile neutrino from supernova. And by the way, at some moment I contacted Georg Graffeld and asked him about that, what he thinks, and he said, obviously, I just showed, when he was published his first papers about that, he said, I showed how one could put a bound if you really have reliable information about the source. But I never said that there are any bounds. This is what he told me in email, and I'm of this opinion as well.
I'm not claiming that. I mean, as you said, it's essentially to indicate there is sensitivity there, right?
But anyway, it's not
combining many different things, right? And it's not going to be perfectly kind of consistent between all the kind of at the confidence level and all these details and so on, right? But I mean, it is, there is a sensitivity here, right? And there would be interesting physics in the supernova in supernova analysis, right? As you're saying, whether this is, I mean, I have to be honest, right? I took any limit from cosmology with a grain of salt, to be honest. also coming from,
Well,
from laboratory
that's the
particle physics,
problem.
right?
That's the
But
problem.
maybe that's something
There
we should kind of go to the discussion later.
Yeah, that's the problem. There are really robust limits from cosmology, and if we mix them with those which are based on so many assumptions, people do what you just said. They start ignoring all the limits from cosmology, which is also too much. But let's really postpone it for
let's move to the discussion. I actually saved Frank's slide so that we'll show it. I think it's very
but the slides is a very nice summary. So thank you very much.